The different compounds having the same formula but different structural formula, they are called as isomers, and this phenomena is called as isomerism. If you compare these two, the molecular formula will be same, just the arrangement of alkyl groups is different. I can make it ethyl and propyl or butyl and methyl. The carbon atom is further attached to how many carbon atoms? Based on that, you can say it is tertiary, secondary or primary. Hello everyone, this is Ambli Unnikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So today we are back with session 5 of the chapter Organic Chemistry. So in last session we discussed about the naming of organic compounds containing functional groups and the naming of organic compounds with polyfunctional groups. That is, if more than one functional group is present, based on the priority we have to name it as prefix or suffix, right? And then the next one is nomenclature of substituted benzene compounds. We studied mono as well as di-substituted as well as poly-substituted benzenes, right? Now today's session we are going to study the next important topic, that is isomerism. Yes, you might have a basic idea about what is isomerism in your 10th class itself. In detail we are going to study in here, that is isomerism, and then the fundamental concepts in organic reaction mechanism. So when the organic compounds are undergoing reaction, they follow a reaction mechanism. So in detail we have to study the properties and what exactly is happening in the reaction. The bonds are breaking, the bonds are forming, all of that, regarding that we will be studying the reaction mechanism. Right, now starting with the first topic, that is isomerism. So the word iso means something is same here, right? Isomerism, something is same. So let's see what is similar here and what is different here. So isomerism are shown by compounds which is having same molecular formula. Yes, this is important. Yes, they are having the same molecular formula, but what they are differing in? They differ in physical and chemical properties as well as they differ in their structural formula. Okay, so they are differing in structural formula means they will have different, yes, physical and chemical properties. So they are different compounds, not same compound, they are different compounds having same molecular formula. That means the number of carbon, hydrogen and other atoms will be the same. Right, the number of atoms will be the same, that is the molecular formula will be the same, but the structural formula will be different. Hence their physical and chemical properties will be also different. So there are two types that is broadly classified into, yes, that is structural isomerism and stereoisomerism. So the structural isomerism, you can find 4 subdivisions in there, that is chain isomerism, position isomerism, functional isomerism and metamerism. So the chain, position, functional and metamerism comes under the structural isomerism, right? And then the next group is stereoisomerism, right? And they are further classified into geometrical and optical isomerism. So in this chapter, in detail, we will be studying about structural isomerism and the 4 types of structural isomerism as well. Just we'll have a quick idea about stereomerism and we'll not be going into the details of stereoisomerism, that is geometrical and optical, in this chapter. In the upcoming chapter, that is hydrocarbons, in detail we'll be studying about geometric and optical isomerism. Okay, so in this session or in this chapter we'll be only dealing with structural isomerism in detail. So beginning with structural isomerism. So what is structural isomerism? Compounds having same molecular formula but different structural formula are called as structural isomers, and this phenomenon is called as structural isomerism. Okay, so the different compounds having the same formula but different structural formula, they are called as isomers, and this phenomena is called as isomerism. Okay, so they have the same molecular formula, but how their carbon skeleton is present, that is the number of carbon atoms present in the principal chain and in the branches, all those will vary, that is their structure will vary, but the overall molecular formula will be the same. So under which the first category is chain isomerism. The first one is chain isomerism. So compounds with same molecular formula but differ in the carbon skeleton are called as chain isomers, and this phenomenon is called as chain isomerism. So let's take an example and understand. Yes, the molecular formula is C4H10. Okay, C4H10. So for the C4H10, there are various isomers which is possible. So one possible way is this one. That is, all the carbon atoms are arranged in a single straight chain. 1, 2, 3, 4. 4 carbon atoms, and there are no double or triple bonds. So this is an alkane, right? So this is which alkane? It is butane. 4 number of carbon atoms. Right, and as you can see in here, one branch has come here in this particular compound. So what is happening here? This methyl group you can see. Now this is being taken and attached here. Yes, now this methyl group is put as a branch in here. So now the compound that you are getting, is it butane? No, it is not butane, right? It is 1, 2, 3. This is how we number it. So it is 2-methyl propane, right? On the second position, there is a methyl group. So it is 2-methyl propane. But still, what is the molecular formula? It is C4H10. It is C4H10 here as well. If you count the number of carbon and hydrogen atoms in both the compounds, they are the same. But what has happened? The carbon skeleton has changed. That is, in here all the carbons were in the straight chain. Now from here one carbon atom has come here. That is, one methyl group is present as a branch here. This is a substituent now. Right? But the overall molecular formula is same, but the carbon skeleton has changed. So this is called as chain isomerism. And these two are called as isomers. Okay, these two are the isomers, and this phenomenon is called as chain isomerism. So this chain isomerism will be only shown by compounds which is having minimum 4 carbon atoms. 4 or more than 4 carbon atoms can show chain isomerism. Right, moving on to the next one, that is position isomerism. Right, so from the name itself you can say position. The position of the functional group or position of the substituent, when it changes, you get the position isomers. Let's see, the compounds with the same molecular formula but differ in the position of multiple bonds or functional group or substituents are called position isomers, and this phenomena is called as position isomerism. Okay, so the position of the functional group, yes, it can be a functional group. It can be your alkene, alkyne, the double or triple bonds. It can be the methyl, ethyl, that is the alkyl groups also. The position varies. You get 2 different compounds. Now, those 2 are called as the position isomers, and the phenomenon is called as position isomerism. Let's take an example. The first compound you can see, it is, yes, the molecular formula is C4H8. There are 4 carbon atoms and the hydrogen atoms is 8. So in the first example, as you can see, it is a double bond present here. So it is an alkene, right? So if I number it 1, 2, 3, 4 on either direction, I can number it because it is symmetric, right? So 1, 2, 3, 4, it is but, and on the which carbon atom is it present? Second carbon atom. So but 2E. Right. Now coming on to the isomer of this one. This double bond has shifted here. Yes, the position has changed. Now what is the compound I am getting? It is but-1-ene. On the first carbon atom, you will have the double bond. So what has the only change? What has happened here? Yes, it is the double bond shifted to the other position. The position of the double bond has changed. Okay. So it can be a double bond. It can be a triple bond. The functional group can change the position. Right, so those are called as position isomers, and the phenomenon is called as position isomerism. Moving on to the next one, that is functional isomerism. Right, so functional. Yes, from the name itself you can suggest functional group. Something is happening with the functional group. Let's see. Compounds with the same molecular formula but have different functional groups are called functional isomers, and this phenomenon is called as functional isomerism. So they are differing in their functional groups, but their molecular formula will be same. How can this happen? Let's take the example. So the molecular formula is C2H6O. There are 2 carbon atoms, 6 hydrogen atoms and 1 oxygen atom. The molecular formula is same, but the arrangement of the atoms will be different so that you get 2 functional groups. Let's see. So the molecular formula is C2H6O. So in the first example, as you can see, CH3, CH2OH. So it is arranged in this form, you get ethanol. CH3, CH2OH, it is ethanol. Now the same molecular formula, if I arrange it in this form, CH3OCH3, I get an ether. right? Here also and here also the molecular formula is same, that is it is C2H6O. If you count the number of carbon and hydrogen and oxygen atoms, it will be same. Molecular formula is same, but the structure, that is the carbon skeleton, is different. That means here the functional group, what you will get, it is alcohol, so it is an ethanol, right? And in this case it is O, that is which functional group? It is ether. So how do you name it? Methoxymethane. It is methoxymethane, right? So this is the functional group isomerism, that is functional isomerism. Let's take one more example. As you can see here, C3H6O. The molecular formula is C3H6O. So one possibility is CH3, CH2, CHO. Now the functional group here is aldehyde. So how many carbon atoms are there? 3. So it is propanol, right? Now the same molecular formula, I can arrange it in this form also. Now what did I get? A ketone, right? So is this same? No, one is aldehyde, one is ketone, but the molecular formula is same. So CH3COCH3, how can I name it? Is propanon, right? It ends with on, so it is propanon. So this is few examples for functional isomerism, that is molecular formula will be same, but the functional groups will be different based on the arrangement of your carbon atoms, right? Now moving on to the last type of structural isomerism, that is metamerism. So compounds with same molecular formula, okay, in all these cases the first sentence is same, right? Same molecular formula, right? But different alkyl groups are present on either side of the functional group and they are called as metamers, and this phenomenon is called as metamerism. So what is differing in here? The alkyl groups present on either side of the functional group will be different. Okay, let's take the example C5H12O. The molecular formula is C5H12O. Okay, so you can represent it in this form, that is CH3, CH2, CH2O. That is in this side you have a CCC, 3 carbon atoms is there. So this is a propyl group, and here what you can see, this is an ethyl group, right? So this is a propyl and this is ethyl, right? On either side it is different, right? The same, what is the other isomer for this? I can write CH3, CH2, 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 right? Butyl I can write, and on the other side I can have the methyl. If you compare these two, the molecular formula will be same, just the arrangement of alkyl groups is different. I can make it ethyl and propyl or butyl and methyl. Okay, so both are having same molecular formula, just the number of carbon atoms present on either side of the functional group will be different. That is, you get different alkyl groups on either side. Okay, so this is named as ethoxypropane. Okay, ethoxypropane, that is whichever is the smallest alkyl group, number containing alkyl group, that will be named as prefix, and the name will end with the higher alkyl group, that is ethoxypropane. In this case there is methyl group as well as butyl, right? So the prefix will be methoxy and the name will end with butane, methoxybutane. So these two are examples of ethers. So now coming on to the next example, CH3CH3O, and on the other side you have CH2CH3. Okay, so here one alkyl group and here another alkyl group. So here it is 3 carbon atoms, so this is propyl and this is ethyl. Okay, so which one is smaller one? It is ethyl, right? So how do you write it? 2-ethoxypropane, right? 2-ethoxypropane. Right, now the same molecular formula but different arrangement of alkyl groups. It is CH3, only one here, CH3, and then you have other 2 CH3 groups here, methyl groups here, right? On the other side you have 3 methyl groups. So it is 2-methoxy, 2-methyl-propane. So what is metamers or metamerism? Yes, the number of alkyl groups present on either side, that is the alkyl groups present on either side of the functional group will differ, but the molecular formula will be same. So I hope the structural isomerism is clear for you and the examples are also clear. Yes, so you have to remember what the definition is, that is what is chain isomerism, position isomerism, functional isomerism and metamerism, and remember the examples as well. Right, so I hope the structural isomerism is clear. Now moving on to the next one, that is stereoisomerism. We'll be not going into the detail, but we need to understand what is stereoisomerism, right? So they are compounds having the same molecular formula and sequence of covalent bonds, but differ in relative position of atoms or groups in space are called as stereoisomers. So how they are arranged in space, that will be different. That means their molecular formula of course will be same and their structural formula will be also same. That means the covalent bonds, how they are bonded, the bonding will be also same. But they will differ in the position in space. When they are represented in the space, in which direction the bonds are present, all those, the substituents are present, all those will be different. So based on the difference in the position in space, we get stereoisomers, and they are generally of two types, that is geometrical isomerism and optical isomerism, which in detail we'll study in the next chapter. So these names you have to remember, that is geometrical isomerism and optical isomerism. Clear? So the isomerism part is done. Right, now moving on to the next one, that is fundamental concepts in organic reaction mechanism. So generally when an organic compound undergoes a reaction, what and all changes happens to it, that is when the bond is breaking, what type of bond breakage is happening there, bonds are forming, the energy released or energy gained, all of this regarding the details of a reaction taking place, the whole details of it we'll study in reaction mechanism. Okay, so generally when a reaction is taking place, what is happening? There will be an organic molecule. We are studying organic chemistry, right? So a substrate, generally we can also call it as substrate. Okay, so there will be an organic molecule. Yes, there will be some reagent. Yes, it has to react with something, right? So there will be certain reagents and you will get an intermediate state, which is unstable. Okay, you'll get an intermediate state, and from the intermediate state you will get the products. Okay, so the substrate, it will react with some reagents, you'll get an intermediate stage, and then you'll get the products. And with the products, certain byproducts can also be there. Always the desired product will be not the only one which is formed. So certain byproducts will be also there which have to be purified, right? So generally what we can see, there will be an organic compound, then it undergoes reaction with the reagent, forms intermediate, finally it forms products and certain byproducts as well, right? So the substrate is the organic molecule which undergoes a chemical reaction. Substrate means which is the initially organic compound which we have taken, it is called as a substrate. Now reagent, any species which bring about the chemical change in the substrate. Yes, the substrate reacts with which compound, that is called as a reagent. And intermediate is unstable, it's an unstable state. Okay, it's an unstable species formed when a substrate is attacked by the reagent. Okay, so it's an unstable state. Through this state only we will get the products and byproducts. So this is the general representation. Now coming on to the details of it. A sequential account of each step describing details of electron movement, the energetics during bond cleavage and bond formation, and the rates of transformation of reactants into products is referred to as reaction mechanism. So the details about all this movement of electrons, the energy release and energy absorption. As you can see here, details of electron movement, the energetics during bond cleavage, right? Bond cleavage means bond breaking, and bond formation. How much energy is released or how much energy is gained. Then the rates of transformation is reacted to products. That means how much fast or how slow the reaction is taking place. So based on all of that, we'll get the details in reaction mechanism, right? The knowledge of reaction mechanism helps in understanding the reactivity of organic compounds in their synthesis, right? And the fission of covalent bonds explains how reaction takes place. So fission means breakage. So what do we know? When a reaction is taking place, there will be certain bonds which is broken. So what type of cleavage or fission is taking place? Based on that, we can predict the reaction mechanism. Okay, so now in detail we are going to study about the different types of fission of covalent bond. That is fission of covalent. So that is, the word fission means the cleavage or the breaking of the covalent bond. So this can happen in two types. In detail we are going to study that. The organic reactions involve the fission of covalent bond, and the fission or cleavage or breaking of covalent bond can take place in two ways. One is homolytic fission and the other one is heterolytic fission. Okay, homolytic fission and heterolytic fission. So first we'll start with homolytic fission. So during homolytic cleavage of a covalent bond, each atom or group attached to that bond gets one electron of the shared pair. So covalent bond means what? Sharing of electrons will be there, right? So as you can see here, if there is a covalent bond between A and A, one electron is contributed by A, another electron is contributed by the other atom, right? Both of them are contributing one electron. Right, and these two electrons will be shared between them. So now what we are talking about, fission of covalent bond. When it is breaking, what happens is in homolytic cleavage, right? In homolytic cleavage, when this bond is breaking, this one electron goes to the atom and the other electron will go to the other atom. They will take up these one electron. So that you can see each of one of them gets one electron of the shared pair. This electron was shared when the bond cleaves, that is homolytic cleavage takes place. One electron will be going into each of the atoms. So as you can see here, if it undergoes homolytic cleavage, each of the atom gets one electron from the shared pair. It will get one each electron. Right. So this one electron containing, that is odd electron containing species is called as free radical. Is this ions? No, it is free radicals, right? It's not having positive or negative charge. As you can see here, there is a dot which is represented for the electron, right? So it is a free radical. It is called as free radical, right? So a free radical is a neutral species, okay, with an odd number of electron obtained by homolytic cleavage of covalent bond. So when homolytic cleavage happens, one electron from the shared pair will be taken up by each of them and it forms a free radical. It is called as a free radical, right? It is a neutral species having odd number of electron. Right? So this is happening in homolytic cleavage. Now the atoms or groups obtained by the homolytic cleavage are known as fragments, and usually homolytic cleavage takes place in the presence of UV radiation or in the presence of organic peroxides. So when does this homolytic cleavage takes place? Either in the presence of UV radiation or in the presence of organic peroxide. Now, homolytic cleavage is performed in the non-polar covalent bond. It can happen only in the presence of non-polar covalent bond. What is polarity or polar covalent bond? If out of the two atoms which share the electrons, one will be more electronegative and the other one will be less electronegative. So, there is a difference in the electronegativity, hence the bond will be polar. So, if in that case, homolytic cleavage can't take place. Homolytic cleavage only takes place if there is no polarity difference. That is, there is no difference in electronegativity. So, in this case, as you can see, both are chlorine atoms. So, both are chlorine means there won't be any electronegativity difference. So, when this bond is undergoing homolytic cleavage, one electron of the shared pair, one each will go to each of the chlorine atom. That is, this paired, the shared pair of electrons, it will undergo homolytic cleavage and each one of them will get the one electron from the shared pair. So now what is formed? Chlorine free radical is formed, right? So I hope it is clear. This is homolytic cleavage. Now coming on to the stability of the free radicals, okay? So the order of stability of free radicals is tertiary, secondary, primary and methyl radical. This is the order of stability of free radicals. We know that yes, once the homolytic cleavage undergoes, we obtain the free radical. Now what is tertiary free radical? Yes, the free radical is present on this carbon atom. The carbon atom is further attached to how many carbon atoms? Based on that, you can say it is tertiary, secondary or primary. So from here you can see the free radical is attached on this carbon atom and this carbon atom is further attached to 3 alkyl groups. That means further 3 carbon atoms. So this is a tertiary free radical, right? The next one is, yes, as you can see, R2CH. Yes, R2CH. That means there is a carbon atom which is having the free radical, right? One is hydrogen, another one is an alkyl group, another one is an alkyl group. That means 2 alkyl groups and 1 hydrogen. So this carbon atom is attached to how many carbon atoms further? 2, right? So this is secondary free radical. Coming on to the third one, it is RC and the other is still hydrogen. right? So the free radical containing carbon, it is attached to only one carbon atom, right? The R stands for the alkyl groups, right? So only one carbon atom. So this is primary. And the last methyl radical, last radical you can see is methyl radical. So the order of stability of free radicals is tertiary, secondary, primary and methyl radical. Okay, and the stability of the free radicals depends upon the bond dissociation energy. If they are having high stability means they are very stable, means it will be very difficult to break the bonds, right? So that means the stability of free radicals is inversely proportional to the bond dissociation energy. Okay, so I hope it is clear. So this is about homolytic cleavage. Now moving on to the next type, that is heterolytic cleavage. During heterolytic cleavage of a covalent bond, both the electrons of the shared pair are taken away by the more electronegative atom. Yes, in the earlier case, homolytic cleavage, both the atoms were the same. That means there is no electronegativity difference. Now we are considering two atoms which are having electronegativity difference. If there is an electronegativity difference, now it becomes a polar covalent bond. So now the shared pair of electrons will be taken by the more electronegative one. They won't be taking one electron each. Both the electrons will be taken by the, yes, more electronegative atom. So as you can see in this example, there is an atom A and atom B which is sharing these two electrons. Now B is more electronegative atom. So what happens? These two electrons B will take. So it will get a negative charge and it becomes an anion, and the A becomes a cation. The shared pair of electrons completely it is taken by B. Yes, you can see here the two electrons is taken by B and A is left with a positive charge, right? Heterolytic cleavage is preferred in polar covalent bond. Why? Polar covalent bond means there is an electronegativity difference, right? So in such cases you can observe heterolytic cleavage. Now for heterolytic cleavage of covalent bond, there should be considerable difference in electronegativity of atoms. There must be a difference in electronegativity, then only the more electronegative atom can take up the shared pair of electrons. So as you can see, there is an alkyl bromide here, CH3Br. This is methyl bromide or bromomethane, right? So in this case, what is happening? There is carbon and bromine, right? How is this represented as CH3Br, right? It is CH3Br. Okay, and what happens when it undergoes this carbon and bromine bond, when it undergoes heterolytic cleavage? Heterolytic cleavage, why? Because carbon is less electronegative than bromine. So what happens? The shared pair of electron, both bromine will take it up. So what happens? CH3, it will become plus. The carbon will get a partial positive charge and the bromine will have a negative charge, and it has taken up the both electrons. So this is heterolytic cleavage, right? So this will happen only in polar covalent bonds which is having a difference in electronegativity between the two atoms. Now coming on to the stability of carbocation. Now what is carbocation? Yes, in this case what you have seen, the species that is found, this is called as a carbocation. Carbo stands for the carbon and cation is positive charge. So when a compound is undergoing heterolytic cleavage, the positive charge which is formed on the carbon atom, that is called as carbocation. Okay, it is carbocation. Now we are going to study about the stability of carbocation, the order of stability. The order of stability is again will be tertiary, then comes secondary, primary and then methyl. Right, okay. So how this, what you are able to see here, CH3 thrice C. What is it actually? CH3, CH3, CH3. 3 CH3 groups and a plus charge. So this is a carbocation, right? So let us consider there was a bromine bond here, a carbon bromine bond here. It underwent heterolytic cleavage and this bromine took up the two electrons and became negative charge, and the carbon will get a positive charge, right? So now the compound which is formed, the species which is formed is called as a carbocation. Now the tertiary carbocation means the carbon atom which is having the positive charge, it is further attached to 3 carbon atoms, 1, 2 and 3. So this is tertiary. Now what is secondary carbocation then? 2 carbon atoms. It is attached to further 2 carbon atoms. That is secondary. That is CH3 twice CH. Now, what is primary? CH3, CH2 plus. So, the order of stability is tertiary, then secondary, then primary. Tertiary will be having the highest stability. Right, okay. So, the carbocation are sp2 hybridized and they have trigonal planar shape. They are sp2 hybridized and have trigonal planar shape. Now, so coming on to the next one, that is in heterolytic cleavage, a carbanion can be also formed. We are clear with carbocation. Right, when the carbon is acquiring a positive charge, it becomes a carbocation. Now, what is carbanion? Let's take this example of CH3, CH3. Right, now in this particular methyl group, I'm writing it as CHH. Right, so there is a carbon and hydrogen bond here. Right, as you can see, carbon and hydrogen bond here. Now, there is a electronegativity difference. Now, which is having more electronegativity? Carbon will be having more electronegativity, right? So, as carbon is having more electronegativity, when this carbon-hydrogen bond undergoes heterolytic fission, carbon will take up the 2 electrons. So, carbon will become negatively charged and hydrogen will move out as H plus. So that is what you can see. CH3, CH3, and from here one CH bond underwent heterolytic cleavage and that comes out as H plus and the negative charge or the 2 shared pair of electrons is taken up by the carbon and this CH2 minus which is formed, it is called as the carbanion. Okay, so when there is a heterolytic cleavage taking place, if the carbon atom is more electronegative, it takes up the 2 electrons and becomes a carbanion. If the carbon atom is less electronegative, yes, the carbon atom will be acquiring a positive charge. So this is carbocation and carbanion, and in homolytic cleavage, you will be obtaining free radicals. Right, so the stability order is also clear, I guess. For free radicals, the order is tertiary, secondary and primary. Same way for the carbocations, the order is tertiary, secondary, primary, the stability order, right? So I hope isomerism and the bond cleavage, that is the fission of covalent bond, that is homolytic and heterolytic cleavage is clear for you. So in the next session, we are going to study what are nucleophiles, what are electrophiles, and then electron movement in organic reactions. How the electrons will be moving in the reactions when it is taking place, and the electron displacement effects in covalent bond. And in the next session, we will be studying the first effect, that is inductive effect. Yes, there are further effects also that you have to study. We'll discuss inductive effect in next session. So I hope what and all we have discussed in this session is clear for you. So that's all for today. Thank you.